Hello, this is your instructor Richard Collins. Welcome to Climate and Climate Change, Unit 14 of ATM101, Weather and Climate of Alaska. In this unit I reviewed the state of our climate, observations of climate change, and forecasts of climate change. In this unit we will distinguish between weather and climate, explore the controls on climate, review observations and forecasts of climate change, examine climate and climate change globally, and examine climate and climate change in Alaska and the Arctic. This lecture supplements our textbook Weather, A Concise Introduction by Gregory Hakim and Jerome Patou with material from the textbook Meteorology Today by C. Donald Ahrens. Weather is the state of the atmosphere at a given time and place. For example, a weather statement would be, it is 57 degrees Fahrenheit at noon in Fairbanks today. The state of the atmosphere is defined by its pressure, temperature, humidity, wind, precipitation, cloud cover, and visibility. Climate is the average of the weather over a long time, typically 30 years. Fairbanks has a subpolar climate with severe winters and short, cool summers, is an example of a climate statement. The purpose of the averaging is not just to provide numbers, but to provide insight into the prevailing pattern of weather at the location. San Francisco, California, and Richmond, Virginia have the same average temperature of 14 degrees Celsius or 57 degrees Fahrenheit, but the climates are very different. San Francisco has a marine climate with humid, mild winters and long, dry, cool summers. Total rainfall is 22.5 inches or 570 millimeters. Richmond has a humid subtropical climate with mild winters and wet in all seasons. Total rainfall is 43.5 inches or 1100 millimeters. San Francisco has a much smaller annual temperature range than Richmond, with milder summers and winters. Climate, like weather, is controlled by several factors. These include latitude, which controls the intensity of sunlight, the distribution of land and water, ocean currents, prevailing winds, position of high and low pressure systems, mountains, and altitude. Alaska extends from 51 degrees north to 71 degrees north, with significant changes in daylight hours between the north and south of the state. Looking at a map of the climate regions of Alaska, we see the boundaries between the regions often follow mountain ranges. There are also distinct maritime regions. The regions change as we travel from south to north. The climate of the Aleutians is controlled by the prevailing winds, and the Aleutian low impacts the climate of the southwest, while the polar high influences the Arctic climate region. In understanding the drivers of climate, we need to understand how energy moves between different parts of the Earth atmosphere system. First, we consider the visible light from the sun and its fate over a year and over the whole globe. A nominal 100 units of sunlight, corresponding to 340 watts per meter squared, of visible energy enters the top of the atmosphere. 19% of that incident light is absorbed by aerosols and clouds. 20% of that light is reflected from clouds. 6% is reflected by the process of scattering from the air in the atmosphere, and 4% is reflected from the Earth's surface. Overall, 51% is absorbed at the ground, 19% is absorbed in the air and clouds, and 30% is reflected back to space. Thus, the Earth atmosphere has a total albedo of 30%. We now look at both the visible solar radiation and the infrared terrestrial radiation. The solar radiation heats the surface of the Earth, 51 units. The surface of the Earth then transfers energy to the atmosphere and back to space by conduction and convection, 7 units, evaporation, 23 units, and emission of terrestrial infrared radiation to the atmosphere, 111 units, and emission of terrestrial infrared radiation to space, 6 units. The atmosphere, both air and clouds, re-radiates both downward to the surface, 96 units, and upward to space, 64 units. The first thing to notice is the amount of heat stored in the Earth's atmosphere. There is more infrared energy exchange between the atmosphere and the surface than there is solar radiation being absorbed by the surface. The second thing is to identify the greenhouse effect. This is the effect the atmosphere has on heating the Earth by absorbing terrestrial infrared radiation that would otherwise be lost to space, 111 units, and then re-radiating it downwards to heat the surface, 96 units. Finally, we recognize that while there might be a global balance, at each latitude there is an imbalance. At lower latitudes, equator of 38 degrees, the sun is higher in the sky and the amount of solar energy increases. The surface is warmer, and while there is more terrestrial radiation emitted by the warmer surface, there is a net surplus of energy absorbed. At higher latitudes, poleward of 38 degrees, the sun is lower in the sky or even absent, and the amount of solar radiation decreases. The surface is cooler, and while there is less terrestrial radiation emitted by the cooler surface, there is a net deficit of energy absorbed. In response, the tropics share their surplus with the polar regions through the ocean currents and storm systems that carry energy poleward. Talking of currents, we now look at the world's ocean currents and dominant pressure systems. First, the pressure systems. The Northern Hemisphere Pacific High and Bermuda Azores High move poleward in July during northern summer. You can see this in the difference between the pressure map for January in the upper left and July in the lower left. The Southern Hemisphere highs also move poleward in January in southern summer, but less than their northern counterparts. In winter, the Aleutian Low and the Icelandic Low appear in the northern hemisphere. The Siberian high appears in winter in the frigid conditions of Central Asia. Thermal lows appear over South America, Africa, and Asia as the land heats up in summer. Surface winds drag surface waters with them, and so the wind systems generate the major surface water currents. The Bermuda Azores High creates the clockwise circulation in the North Atlantic that gives rise to the Gulf Stream, the Canary Current, and the North Equatorial Current. The Pacific High supports the North Pacific Current and the North Equatorial Current. The South Pacific High supports the Peru Current, the South Equatorial Current, and the Antarctic Circumpolar Current. The currents have a major impact on regional climates. The Gulf Stream, or North Atlantic Drift, brings so much heat to Europe that ports in northern Norway stay ice-free in winter, and all of Europe remains tens of degrees warmer in winter than the corresponding latitudes in North America and Asia. The California, Peru, Benguela, and South Equatorial currents cool the coastal waters of California, Chile, Namibia, and Australia, and thus dry out the onshore westerly winds. This maintains the arid regions of central California, the Atacama Desert, the Kalahari Desert, and the Great Australian Desert. So now let's look at the global temperatures in January and identify what processes control the regional temperature patterns. First, how do we know it's January? Well, our big clue is that it's minus 50 degrees Fahrenheit over Siberia in region H. Now let's focus on region B in the southeastern Pacific. Here we see that the isotherms are horizontal following the lines of latitude. This is what we expect from solar heating alone, whereas we move to higher latitudes, the sun is lower in the sky, the sunlight is spread out further on the surface, and heats the surface less. We see a similar pattern in Asia in region I. Thus regions B and I reflect control by latitude and the associated change in solar angle. In regions A and E, we see the effects of land-sea contrast. In the North Pacific region A, the winter land is colder than the winter coastal sea. In South Atlantic region E, the summer land is warmer than the summer coastal sea. In regions D, G, and F, we see the effect of ocean currents. In regions D and G, cold coastal currents carry colder water equatorward along the west coast of South America and southern Africa. We see the colder isotherms move equatorward along the coast. In F, a warm ocean current from the Gulf of Mexico carries warm water northeastward to Europe. We see the warmer isotherms move increasingly polarward as we travel eastward across the North Atlantic. In the eastern Siberia region H, we see the effect of low solar elevation with short days and long winter nights. Under high pressure and clear skies, the ground cools to space and gets extremely cold. The cold air sinks and reinforces the high pressure and the clear skies. In the Andes region C, we see the effects of elevation. Aconcagua, South America's highest peak, rises to 6,961 meters. Regions at high elevation have less atmosphere above them, the air is thinner, and the air is drier. All this means the atmosphere provides less greenhouse effect to keep the surface warm. We see the colder isotherms snake northward along the Andes with sharp temperature gradients echoing the elevation contours of the mountains. In the Australian desert region J, we see the effect of low cloud cover allowing intense heating of the surface. Region J is in the subtropics under the descending side of the Hadley cell. There is persistent high pressure and clear skies. Now we look at precipitation. Our three-cell circulation results in rising air at the tropics in the intertropical convergence zone due to the rising air of the Hadley cell, and at mid-latitudes at the polar front due to the rising air of the Ferrel cell. Our main rainy regions are at the ITCZ and the polar front. However, temperature also plays a role. As we head poleward, air cools and becomes less humid as its capacity to hold water vapor decreases. Thus, the climate gets progressively drier as we travel poleward. Let's now look at the distribution of annual precipitation around the world. In regions A and B, we see high precipitation in coastal mountain ranges. The onshore winds are very humid. Rising over the mountains, they cool, the water vapor condenses to liquid water, and it rains. In the equatorial regions of E, I, and L, we are at the latitude of the intertropical convergence zone and the rising side of the Hadley cell. There are high levels of precipitation that give rise to the rainforests of Brazil, the Congo, and Indonesia. In the subtropical regions of H and M, we are in the falling branch of the Hadley cell. There is little precipitation, and the Sahara and Great Australian deserts are found here. In the coastal regions of C, F, and J, cold currents on the eastern side of their oceans cause onshore winds to cool and lose their moisture. The deserts of California, Chile, and Namibia are found here. In the regions D and K, we see the effects of high and low pressure systems. In region D, the clockwise circulation around the Bermuda Azores High brings moisture from the Atlantic Ocean and Gulf of Mexico into the southeastern United States. In region K, we see the high precipitation associated with the monsoon. During the monsoon, the formation of a thermal low in summer over south-central Asia results in onshore southerly winds that carry moisture from the Indian Ocean into South Asia, not unlike a giant sea breeze. In the Western Europe region G, we see the effects of the prevailing winds carrying moisture from the North Atlantic. Unlike region B, the mountains in Europe are not as steep or high as in Western North America, and so the precipitation is less in G than in B. Let's now talk about how the climate has changed over the past 800,000 years. 800,000 years represents about how far ice cores can see into the past, though current researchers are trying to push that back to 1.2 million years. The limitation is the length of the ice cores. The length is limited both in terms of how deep we can drill as well as the depth of undisturbed ice. The temperature record shows variations about 100,000 years, 41,000 years, and 23,000 years that are due to Milankovitch cycles. The eccentricity of the Earth's orbit changes over periods of 100,000 years. Currently, our orbit is relatively circular, but it can be much more elliptical, giving more extreme seasons. The Earth precesses are wobbles like a spinning top over a period of 23,000 years. In 11,000 years, the Earth will be closer to the Sun in July than January, and seasons will be more extreme in the Northern Hemisphere. The Earth changes its tilt over a period of 41,000 years. The tilt can vary between 22 and 24.5 degrees, with today's value being 23.5 degrees. The smaller the tilt, the less seasonal variation. Cooler summers promote growth of ice sheets and glaciers, so as the Milankovitch cycles progress, they add and subtract their effects and give rise to variations in the ice sheets, thus variations in the Earth's albedo and energy balance, and this is what causes the average temperature of the planet to change over time. Analyzing the gases in the ice cores, we can see that warmer periods correspond to higher carbon dioxide levels and colder periods to lower carbon dioxide levels. We see times where the increase in carbon dioxide follows the increase in temperature. This is what we might expect from increased biological activity during warmer periods. This is a different scenario than our current climate change, where an increase in carbon dioxide is driving a following increase in temperature. How do we measure temperature from bubbles of gas in an ice core? This technique uses the fact that oxygen exists in three isotopes. Oxygen exists as oxygen-16, about 99.76%, oxygen-17 at 0.04%, and oxygen-18 at 0.2%. We will ignore oxygen 17 due to its very small abundance. So water, or H2O on Earth, can be slightly lighter or heavier based on whether it is an oxygen 16 or oxygen 18 atom of oxygen. The idea is that oxygen 18 water condenses faster than oxygen 16 water. So air traveling from the equator to the poles rains out its oxygen 18 water at lower latitudes, and the water getting to the poles is higher in oxygen 16 water. During colder periods, the O18 water rains out more completely, and the polar ice sheet is even higher in O16 water. In warmer periods, more oxygen 18 water gets to the poles and freezes, so polar ice is higher in oxygen 18 water. Thus, we can determine the relative warmth and coolness of the Earth over hundreds of thousands of years. Scientists have used a combination of tree rings, corals, ice cores, historical records, and thermometers to reconstruct the climate record over the past 1,000 years. There have been several distinct warm and cold periods within that 1,000 years. The medieval warm period extended from 800 to 1200, while the Little Ice Age extended from 1300 to 1850. The Maunder Minimum, where the number of sunspots on the sun was much lower than usual, extended from 1645 to 1715. The sun emits less energy when the number of sunspots decreases. The Little Ice Age was not uniform around the globe. It reached its coldest period in the Pacific, Europe, and North America in different centuries. This is unlike the current global warming that sees temperatures rising steadily around the world. These regional effects are seen in the differences between the global mean temperatures and the Northern Hemisphere mean temperatures. We see sharp minima in the Northern Hemisphere temperatures around 1350 and 1450. Extreme cold winters were recorded in Britain and Ireland in the winter of 1338-39, with deep freezing of rivers and holding of winter events on the rivers that were unusual. In the period of 1433 to 1435, there was one severe cold winter recorded in Britain and Scotland. The Little Ice Age is understood to have arisen from a variety of factors that include repeated volcanic eruptions and reduced solar energy. The cooling was then further enhanced by the lowering of the albedo due to increased ice cover. The cooling impact of volcanic eruptions is well documented. Volcanic aerosols that reach the stratosphere stay aloft for a long time and reflect solar radiation back to space. Mount Pinatubo in the Philippines, 15 degrees north, 120 degrees east, erupted on the 15th of June 1991. Volcanic effluents were injected to altitudes of over 30 kilometers. The aerosol cloud circled the Earth in about 3 weeks, and the cooling effects of the volcanic aerosol peaked in 1992. The record of carbon dioxide since the late 1950s shows the gas's unrelenting rise. Observations from Mauna Loa on the Big Island of Hawaii represent the global conditions. The island is in the middle of the Pacific, about 4,200 kilometers or 2,600 miles south of Kodiak Island, and about 4,000 kilometers or 2,500 miles from Los Angeles. The mountain is 13,680 feet or 4,170 meters above sea level. Thus, the air sampled on Mauna Loa is not contaminated by local industrial sources. Our current global warming is indeed global and arises from the global increase in greenhouse gases. Sites across Alaska all show warming over the 71 years from 1949 to 2020. In Alaska, the greatest warming is found in the Arctic regions, while the smallest increases are found in the maritime regions. The increase in temperature in Alaska is greater than over the whole world. The greater warming in the polar regions is called polar amplification. It is due to the fact that as the polar regions warm, their albedo increases, allowing absorption of more solar radiation. It is a classic positive feedback. The fact that the Earth is warming from year to year means that the Earth is gaining more energy than it is losing each year. This imbalance, called the Earth Energy Imbalance, or EEI, has been determined from measurements and models and shown to be increasing in time. The current estimate puts the imbalance at 0.76 watts per meter squared in the 2006-2020 time period. Most of that heat has gone into the ocean, about 89%, followed by the land, 5%, cryosphere, 4%, and the atmosphere, 2%. The total energy absorbed is 381 zetajoules, or 10 to the 21 joules, over that period. Representative concentration pathways were developed by the Intergovernmental Panel on Climate Change to represent a wide variety of scenarios without getting into the specifics, e.g. increased coal power plants, etc. 4 pathways are used, ranging from 2.6 watts per meter squared to 8.5 watts per meter squared. The pathways include the effects of emission of greenhouse gases, air pollutant concentrations, and land use. RCP 8.5 yields 1,370 parts per million carbon dioxide by 2100. In comparison, RCP 6 yields 850 parts per million, RCP 4.5 yields 650 parts per million, and RCP 2.6 yields 490 parts per million. RCP 8.5 has been termed business as usual, but this is somewhat controversial as it assumes no serious climate action. However, it is still accepted as a worst-case scenario. The maps of the future temperature change reflect the variability we have seen in Alaska. In both RCP 2.6 and RCP 8.5, the Arctic warms more than the rest of the planet. Generally, the land warms more than the sea, and there is considerable variation across the continents. This geographic variability reminds us that the Earth is not a bathtub where the temperature rises uniformly. This geographic variability may also have considerable effect on the pattern of the general circulation, changing the path of jet streams and storm tracks. One of the great uncertainties is if any changes occur in the ocean circulation. A primary concern is the disruption of the Gulf Stream, where global warming could cause Europe to cool significantly. Most climate and reanalysis models have a horizontal resolution of over 100 kilometers. Thus, each data point represents the average over 100-kilometer long square. While this is useful for studying the general circulation, it is not useful for understanding possible change at the local level at tens of kilometers. It may not be useful at all for understanding mountain weather, where the terrain changes dramatically over scales of 11 to 10 kilometers. Scientists resort to downscaling. In downscaling, the meteorologists nest a high-resolution, large-scale model that covers a local area inside a low-resolution, small-scale global model. The meteorology at the boundary is defined by the global model, while the local model determines the small-scale variations within the local region. Downscaled maps of Alaska that forecast the future climate are created by meteorologists for farmers and gardeners to support agriculture in Alaska. The maps are maps of U.S. Department of Agriculture, or USDA zones, based on the 30-year average temperatures. In the upper left, we have 1980 through 2009. In the upper right, 2010 through 2039. Lower left, 2040 through 2069, and lower right, 2070 through 2099. USDA zones are based on the minimum temperature expected in that region for the year. Minimum temperatures set the survival threshold for most plants. Zone 1A corresponds to a minimum temperature of -60 to -55 Fahrenheit. The zones increase by 5 degrees Fahrenheit through 1B, 2A, 2B, and on to Zone 10B, corresponding to a minimum of +35 degrees Fahrenheit to 40 degrees Fahrenheit. We see that over time, Fairbanks transforms from Zone 2B, comparable to northern North Dakota, to Zone 4A, comparable to central North Dakota, to Zone 5A, northern Iowa, and finally arriving at Zone 6B, comparable to southern Illinois. As you look at the maps, consider how the geographic pattern of the zones changes in time. Between 2040 to 2069 and 2070 to 2099, the pattern of zones in northern Alaska changes significantly as the whole north coast becomes the same zone as southeast Alaska. This reflects that the Arctic Ocean has become ice-free by that time. The changes in colors also show how climate change accelerates over time with bigger jumps in climate zone as climate change progresses. This slide is given as a reference to show how the zones forecast for Alaska compare with current zones in the lower 48, Hawaii, and Puerto Rico. This map provides the comparison for me to say that Fairbanks transforms from the zone of northern North Dakota to central North Dakota to northern Iowa and finally to southern Illinois. The zone colors give a vivid reminder of how the U.S. Southeast is under the moderating influence of the Gulf of Mexico, while the upper Midwest is under the influence of Canada. Summing up this unit, 1. Climate of a region is controlled by geographic and meteorological phenomena. 2. Signatures of climate controls are evident in both global temperature and precipitation maps. 3. Ideally, the Earth and atmosphere is in radiative balance between incoming solar radiation and outgoing terrestrial radiation over the whole year. 4. The solar, or visible and shortwave, input does not balance the terrestrial, infrared, or longwave output at each latitude. 5. The transfer of heat within the Earth atmosphere system is larger than the amount of solar energy incident on the atmosphere. 6. Earth's long-term temperature record can be reconstructed from ice core measurements. 7. Variations of temperature and carbon dioxide are correlated. Over the long term, rises in temperature have sometimes preceded rises in carbon dioxide. 8. The current global warming is driven by increases in carbon dioxide resulting in the warming. 9. The climate record also shows impact of variations in solar activity and volcanic eruptions. 10. The climate of Alaska has warmed across the state by a greater amount than the global average, indicating polar amplification. 11. There is an Earth energy imbalance that indicates there is more solar radiation being absorbed than terrestrial radiation being emitted each year, and this is increasing over time. 12. Models indicate that the Earth atmosphere will continue to warm with strong regional variations in temperature. These regional changes may cause changes in our weather patterns. 13. A rise in the global temperature may not seem dramatic, but the regional variations are significant.